Have you ever just looked at a world map and thought, wait a minute, this looks like a giant broken jigsaw puzzle, like the pieces could almost slot back together? Well, you're not wrong to think that. Turns out our planet's surface isn't static at all. It's this incredibly dynamic, ever-shifting puzzle. And today we're going to put some of those pieces together.
And this right here is the first, most glaring clue in our whole geological mystery. I mean, just look at the coast of South America and the coast of Africa. It's an almost perfect match. It's so uncanny, it just forces you to ask the question, is that just a wild coincidence, or is it a clue to something way, way bigger?
To answer that, we've got to go back in time, over a century ago, to meet the first real detective on this case. A German scientist named Alfred Wegener, who came up with an idea that was, for his time, completely radical.
So, way back in 1912, Wegener drops this bombshell of a theory, continental drift. He basically said that about 300 million years ago, all the land on Earth was smushed together into one giant supercontinent. He called it Pangaea. And over millions and millions of years, Pangaea cracked apart, first into two big chunks, Laurasia and Gondwana land. And then those pieces just kept drifting until they ended up where they are today.
And look, Wegener wasn't just spitballing here. He had receipts. Beyond the obvious jigsaw fit, he found identical rock types and even mountain chains on opposite sides of the Atlantic Ocean. He found fossils of the exact same land animals, like this little guy Mesosaurus in both South America and Africa. Now, how does a reptile that can't swim cross an entire ocean? He even found traces left by ancient glaciers in places that are now scorching hot tropics.
But here's the kicker. Despite all this evidence, the scientific community at the time basically laughed him out of the room. Why? Because while Wegener had the what, he was missing the how. He couldn't come up with a force, a mechanism powerful enough to shove entire continents across the globe. So for decades, his incredible idea was just shelved.
But a good puzzle never really goes away. Decades later, with brand new technology that let us map the ocean floor, scientists finally found it. They found the missing piece, the engine that drives the whole system.
And this was the game changer. See, Wegener thought the continents were like ships plowing through the ocean floor. The modern theory, plate tectonics, which really came together in the 1960s, showed us that's not quite right. It finally gave us the how. The continents themselves aren't doing the moving. They're more like passengers on these huge floating rafts called plates. And the engine? It's powered by the intense heat from inside the Earth itself.
So here's the main idea. The Earth's hard outer shell, the lithosphere, isn't one solid piece. It's actually cracked into about a dozen major plates, kind of like a broken eggshell. And these massive plates are floating on a layer of hot, semi-molten rock called the asthenosphere, which flows incredibly slowly, kind of like thick, hot caramel.
So what's pushing them? Deep inside the Earth, heat from the core causes molten rock to rise, spread out, cool, and then sink back down. It creates these massive, slow-moving circular currents. Think of them like giant conveyor belts, and these conveyor belts are what drag the tectonic plates across the surface. This was the powerful force Wegener was looking for.
Okay, so if you've got these colossal plates constantly on the move, what happens when they bump into each other? Well, that's where all the action is. Earthquakes, volcanoes, the creation of entire mountain ranges. It all happens right there at the plate boundaries.
And there are pretty much three ways they can interact. At divergent boundaries, they pull away from each other, like at the Mid-Atlantic Ridge, creating new crust. At convergent boundaries, they smash into each other, buckling up to form huge mountains like the Himalayas. And at transform boundaries, they just grind past one another, like the San Andreas Fault in California, building up a ton of stress.
Let's just zero in on those collisions for a second, because they are responsible for some of the most spectacular scenery on the planet. The forces at work here are just mind-boggling. They literally build mountains from the ground up.
When two continental plates collide head-on, all that rock has nowhere to go but up. The unbelievable compression force squeezes and bends the crust, creating massive wrinkles and waves. We call this process folding, and it's exactly how the world's greatest mountain ranges got there.
And what's really cool is you can actually see the age of these mountains. Old fold mountains, like the Appalachians, are ancient. They formed hundreds of millions of years ago, and they've been worn down and rounded by ages of erosion. But the young fold mountains, like the Himalayas, they are sharp, jagged, and they're still being pushed up. They're literally still growing, right now.
Of course, plates don't just push together, they also pull apart.
When tension stretches the crust, it can crack along lines we call faults. And sometimes, a huge chunk of land between two of these cracks will just drop down. And boom, you get a massive valley. This is called faulting, and it's precisely what's creating the Great Rift Valley in East Africa.
Now, building mountains is a slow burn process. It takes millions of years. But sometimes the result of all this plate movement is anything but slow. Sometimes the energy release is sudden, violent, and absolutely world-shaking.
An earthquake is basically what happens when all that stress that's been building up along a fault line finally lets go. The spot deep underground where the rock physically breaks or slips is called the focus, and the point right on the surface directly above it, that's the epicenter. That's where the shaking is going to be the most intense. And we measure the sheer power of these things using the Richter scale. Now, you got to understand, this isn't a simple 1 to 10 scale. It's logarithmic. That sounds complex, but all it means is that going from a magnitude 5 to a magnitude 6 isn't just one step up. The shaking is 10 times stronger, and it releases about 32 times more energy. That's the difference between a good shake and a complete disaster.
So where does all this happen? Well, the vast majority of it is concentrated in one area, a massive horseshoe-shaped zone that wraps around the Pacific Ocean. You've probably heard of it, the Ring of Fire. It's where the giant Pacific plate is bumping and grinding against a bunch of other plates, and it's responsible for most of the world's earthquakes and volcanoes. It is the geologic hotspot.
And wherever you have these weak spots in the crust, usually right at these plate boundaries, molten rock or magma can find a path to the surface. And that's how you get a volcano. They come in all shapes and sizes, from those broad, flat shield volcanoes to the classic pointy-peaked stratovolcanoes like Mount Kilimanjaro.
Which brings us right back to the beginning. That simple, nagging question about why Africa and South America look like they fit together, it all leads to this single, elegant, incredibly powerful theory: plate tectonics. It explains everything: the drifting continents, the towering mountains, the deep valleys, the violent earthquakes, and fiery volcanoes that constantly reshape our world.
And I think that's the real takeaway here. The Earth isn't a finished product. It's a work in progress. The very same forces that ripped Pangaea apart and shoved the Himalayas into the sky are still humming along, right now, deep beneath our feet. And that just leaves you with one final thought, doesn't it? If this is the world these forces have built so far, what on earth will they build next?